All right, let's talk about how AI sees the world. But we're not just talking about an AI that can slap a label on a photo and say cat or dog. No, we're going way deeper. We're going to figure out how it can trace every single pixel of that cat, from its whiskers all the way to its tail, with a precision that is just mind-blowing.
So it all boils down to this one question. How on earth does a computer go from just seeing a photo of, say, your pet, to perfectly understanding the exact boundary of every little thing, right down to the single pixel? You know, tracing the fur, the ears, it feels like it should be impossible. It looks like magic, but it's really just an incredibly clever piece of engineering.
Okay, so this is where it all begins, with a totally normal picture. To you and me, that's a cute animal. But to a computer, it's just a giant grid of numbers, a spreadsheet of color values. It has no idea what a dog is or what the background is. This is our starting point.
And this is the goal. A perfect pixel-for-pixel map, where every single tiny dot is labeled either pet or not a pet. This amazing map is called a segmentation mask, and we are about to pull back the curtain and see exactly how it's done.
So first, let's get into the problem itself. I mean, why do we even need this crazy level of detail? Isn't just knowing it's a cat or a dog good enough? Well, it turns out that for some of the most important jobs we want AI to do, knowing what is in the picture is only half the battle. You absolutely have to know where it is.
And that brings us to the official term for this, image segmentation. It's exactly what it sounds like, assigning a category to every single pixel. We're not just drawing a lazy box around an object. We are creating this incredibly rich, detailed map of the entire scene. And this is totally essential for things like medical imaging or self-driving cars.
See, here's the fundamental issue. Traditional AI vision models, the ones that are great at just labeling things, have a big problem. To figure out what's in a picture, they're designed to shrink it down over and over again. They basically throw away all the fine details to focus on the big concept. Great for saying, yep, that's a cat, but absolutely terrible for segmentation, where those tiny details are everything.
So, there's the challenge, right? How do you get the best of both worlds? How do you get that high-level big-picture understanding and the pixel-perfect detail of where everything is? Well, enter our hero, the UNET architecture. It's this beautiful, elegant model, and yeah, it's named that because it's literally shaped like the letter U. So the journey through the UNET starts by going down the left side. This is called the encoder, and it acts just like one of those traditional networks we just talked about. It squishes the image down, making it smaller and smaller, but getting smarter and smarter about the high-level ideas, the what in the picture.
Then we get to the very bottom of the U. This is the bottleneck. At this point, the image is as small and abstract as it's going to get. This is the moment of maximum understanding, where the model has sort of figured out the overall vibe and context of the entire image. Okay, so from that point of maximum understanding, we start the climb back up the right side of the U. This is the decoder path, and it does the exact opposite of the encoder. It starts making the image bigger again, adding back the resolution, layer by layer, to build that super detailed map of where everything is located.
But wait a second. If you just shrink an image down and then blow it back up, you lose all the sharp details. It would be a blurry, useless mess. The information you lost on the way down is just gone. But UNET has a secret weapon to fix this, and honestly, it's the entire reason this thing is so brilliant.
They're called skip connections, and you can think of them like bridges, or maybe even informational shortcuts. They create a direct pathway from the down path over to the up path. They literally take the rich, detailed information from the early layers and zap it directly across to the corresponding layers that are trying to rebuild the image.
And the difference this makes, I mean, it is literally night and day. Without those connections, the decoder's just kind of guessing, trying to fill in the blanks, and you get a fuzzy, imprecise blob. But with the skip connections, it gets all that precious, high-res detail back, and that lets it draw a crisp, clean, and incredibly accurate outline.
You know, the original paper that introduced UNET put it perfectly. These connections allow the network to combine the what, that global semantic information from the bottom, with the where, the fine-grained spatial details from the beginning. It really is the best of both worlds.
Okay, so that's the theory. It sounds awesome on paper, right? But does it actually work? Let's look at the payoff. Let's watch UNET in action as it's actually learning.
So check this out. We can actually watch the model get smarter. After just 5 rounds of training, what they call epochs, the prediction is, a pretty rough blob.
But fast forward to 20 epochs, and whoa, that outline is getting way more refined. And then, after 30 epochs, it's nearly perfect. It's incredibly close to the actual outline. The final model gets over 82% validation accuracy, which is just clear proof that this whole idea works, and it works really well.
And this is so much bigger than just pet photos. This technology is a game changer in so many fields. We're talking about medicine, where it can outline a tumor in a CT scan with pixel-level accuracy. For self-driving cars, it's what identifies the exact edge of the road or a pedestrian. It's used to analyze satellite images, to help robots see. I mean, anywhere a machine needs to understand not just what it's looking at, but precisely where it is.
So I'll just leave you with this one thought. We've just seen how a machine can go from a simple photo to tracing the boundary of a single strand of fur. Think about that. This kind of granular, detailed understanding, it just opens up a whole new world of possibilities. So the only real question is, what boundaries will this technology redefine next? Thanks for tuning in.